When you look at a mountain range, it just seems so permanent, right? So immovable. But the truth is, these incredible structures are actually the result of some seriously colossal forces that are constantly folding, cracking, and just totally reshaping our planet's crust. And they've been doing it for millions and millions of years. So let's pull back the curtain on this epic story of how the Earth literally builds mountains.
Okay, to really get our heads around this, we have to think in geological time, which is just vast. The Earth has gone through at least 9 of these massive mountain-building periods, which geologists call orogenies. What you're seeing here are the 3 most recent acts in this planetary drama. We start way back with the Caledonian, which gave us the ancient, weathered mountains you see in places like Scandinavia. Then came the Hercynian, forming ranges like the Appalachians. But the real showstopper, the recent one, was the Alpine orogeny. And when I say recent, I mean just 30 million years ago. That's a blink of an eye in geological terms. And this is the one that thrust up the giants we know today: the Alps, the Rockies, and of course, the mighty Himalayas.
So, how does a planet actually build a mountain range? Well, the most common way is surprisingly simple. It all starts with a process called folding. I want you to imagine a rug on a smooth floor. If you push both ends of that rug toward the middle, what happens? It wrinkles up, right? That is exactly what happens to the Earth's crust, just on an absolutely massive scale, to create what we call fold mountains.
Now you're probably wondering what's causing this immense squeeze. Well, it's not just one thing. It's a combination of these incredible deep Earth stresses. We're talking about the sheer weight of rocks piling up over eons, slow-moving currents churning in the molten mantle right beneath the crust, magma forcing its way up, or even the entire planet subtly expanding or contracting. All of these forces work together to create this massive mountain-building compression. And this diagram just captures the result perfectly. On the left, you see these neat, horizontal layers of rock, just like they were laid down over thousands of years. But then you apply those immense compressive forces we just talked about, and you get the image on the right. The crust has literally wrinkled and shortened, creating a whole series of massive waves. These waves are the fundamental building blocks of a fold mountain range.
Okay, let's get a couple of key terms down because they're actually pretty simple. Those upward arching folds, the very peaks of those rock waves, those are called anticlines. So next time you're looking at the top of a mountain ridge that looks like a big wave, you can be like, hey, that's an anticline.
And of course, for every upfold, there has to be a downfold. It just makes sense. The opposite of an anticline is a syncline. These are the troughs or the valleys in those rock layers. So really, every great fold mountain range is just this beautiful undulating series of alternating anticlines and synclines. Peaks and valleys written in stone.
But as you can imagine, the Earth's forces are rarely so neat and tidy. With enough pressure, these simple folds can get incredibly complex, totally distorted. As this diagram shows, a simple symmetric fold can get pushed right over into an overfold and then a recumbent fold that's literally lying on its side. In the most extreme cases, the rock can actually fracture and slide over itself, creating this massive displaced structure called a nap. This is geology at its most intense.
So what are the defining traits of these fold mountains? Well, for starters, they are the youngest and loftiest on our planet. Think Mount Everest in the Himalayas. They're typically sculpted from sedimentary rock that was once at the bottom of an ancient ocean. You'll often find them in these long, narrow, arc-shaped ranges. And this is crucial. The intense pressure and heat involved in their creation also cooks up rich mineral resources like tin, copper, and petroleum, which makes them incredibly important to us.
All right, let's switch gears and move on to our next type of mountain. We've just seen what happens when the Earth's crust is flexible enough to bend and fold. But what happens when the rock is too brittle, when it can't bend under all that strain, and it just cracks?
This slide sums up the difference perfectly. Bending under pressure creates folds and, you guessed it, fold mountains. But cracking, a process called faulting, creates an entirely different structure, the block mountain. So this isn't a story of compression and squeezing, it's a story of tension, fracture, and massive blocks of land on the move.
This diagram shows a totally different set of forces at play. Instead of compression, we're now looking at tensional forces. That means forces are literally pulling the crust apart. This stretching causes massive cracks, or faults, to develop. And as the crust keeps pulling apart, huge blocks of land caught between these faults can either be forced up or drop down.
Now, when one of those massive blocks is left standing high or is actively pushed upwards between two faults, it's called a horst. And that horst is the block mountain. They often have these incredibly steep, cliff-like sides and a pretty flat top. A classic example of this is the famous Black Forest in Germany.
On the flip side, when a block of land drops down between two faults, it forms a graben. You might know this better as a rift valley. And the most spectacular example on our planet is the East African Rift Valley. It's this colossal graben system that's actively tearing a continent apart, and it stretches for thousands of miles. So it's a simple pairing, really. A horst is the mountain, and a graben is the valley.
Okay, so we've covered the geology of bending and breaking. Our final two mountain types are best understood as simple processes of addition and subtraction. One type is built from the ground up, literally adding material to the landscape, while the other is what's left behind after everything else has been subtracted away.
First up is addition. Volcanic mountains are pretty much exactly what they sound like. They are built up layer by fiery layer from material that's been ejected from deep inside the earth. We're talking molten lava, scorching ash, cinders, and dust. All of it erupts and piles up around a central vent, creating that classic, iconic cone shape. Just picture the beautiful symmetrical cones of Mount Fuji in Japan or Mount Mayon in the Philippines.
And finally, we have subtraction. See, residual mountains aren't really built at all. They're the survivors. They are what remains of an ancient plateau or landmass after thousands, even millions of years of relentless erosion, what geologists call denudation. Rivers, glaciers, wind, and rain act like sculptors, just tirelessly wearing away the softer surrounding rock, leaving only the most resistant, hard rock standing proud as these isolated peaks.
So, what's the big takeaway from all this? Well, from the slow, gentle wrinkling of the crust to violent fractures and explosive volcanic eruptions, the surface of our planet is anything but static. These four processes are a powerful testament to just how dynamic and alive the Earth truly is, right beneath our feet. So let's do a super quick recap to lock it all in. We've got fold mountains, born from compression and bending, like the Himalayas. Then we have block mountains, created by tension and cracking, like Germany's Black Forest. After that, volcanic mountains, built by the addition of material from below, like the iconic Mount Fuji. And finally, residual mountains, sculpted by the subtraction of everything else through erosion, like Mount Matadok in the US.
And that leaves us with a truly fascinating final thought. Right now, as we're speaking, the Himalayas are still getting taller. The East African Rift is slowly tearing a continent in two. The very same colossal forces that built all the mountains we've just discussed are still powerfully at work, reshaping our world as we speak. So the real question isn't just if there will be a next great mountain range, but where will it rise, and what on earth will it look like when it finally breaks the sky?